In section 2, we're going to go ahead and look at our chi-square test for homogeneity. So when we did two proportion Z procedures, so confidence intervals and significance tests, it allowed us to compare the proportion of successes in one or two populations with two proportions. And the chi-square statistic will allow us to compare the proportions of successes across several populations or treatments instead of just one or two. So we need a new statistical test for this, and that is called the chi-square test for homogeneity. So we're going to start with kind of looking at an example to kind of work our way through this. So we have that after turning the age of 18, do males and females differ in their living arrangements with their parents? We select two separate random samples of 200 males and 150 females who are between the ages of 18 to 20 to determine where they live, and the results are in our table. So either they live with their parents, in an apartment, or in a dormitory. So statistical methods for dealing with problems involving multiple treatments or populations usually have two parts. The first part is an overall test to see if there's good evidence of any differences among the parameters that we want to compare, and then a detailed follow-up analysis to decide which of the parameters differ and to estimate how large the differences are. And the overall test uses our chi-square statistic and distributions. So to perform a test, our null hypothesis would be there is no difference in the distribution of categorical variables for several populations or treatments. And our alternative is that there is a difference in the distribution of categorical variables for several populations or treatments. So if we're going to write our null and alternative hypothesis for our example, our null hypothesis is there is no difference in the distributions of living arrangements among males and females. And the alternative hypothesis is that there is a difference. So there is a difference in the distributions of living arrangements among males and females. So unfortunately, there's not really a way to write this mathematically. We can really only just write it using words, mainly because it would be a lot longer and unnecessary to convert this to symbolics. Couple things here is that for the alternative hypothesis, you could incorrectly state all of the proportions are different, and that's not the same thing. And you want to think about it this way. The opposite of all of them being equal is that some of them are not equal. So we're not necessarily saying all the proportions are different, just that some of them are not equal to each other. So we compared observed counts in a two-way table with the counts we would expect if the null hypothesis were true when we performed a goodness of fit test. To find the expected counts, we start by assuming that the null hypothesis is true. In our example, we're assuming that there is no difference between males and females in their living arrangements. So the proportion of males is the number of males we surveyed, 200, over our total number of people, 350. And for our females, it's going to be 150 over 315. So we would expect this proportion to be the same across all living situations. This does not mean the expected counts will be the same. We want the proportion to be the same. So our observed counts are from our table. For our expected counts, we then take our proportion of female, which is 150 over 350, and we need to multiply it by the observed total number who live with their parents, 133, which gives us 51.857. For in an apartment, we'll do 150 over 350 times the total who live in an apartment, 56, which gives us 24. And then lastly, for our dorm, 150 over 350 times 161, which gives us 74.143. So for males, we're going to do their proportion, 200 over 350 times our totals. So first one is times 133, which gives us 69.143. Then we do 200 over 350 times 56, which is 32. And then lastly, 200 over 350 times 161, which is 98.857. So to find your expected counts, if you kind of want to think about it as a formula, the expected count of any cell in a two-way table is going to be your row total times your column total over your table total. So we think like my row total for female, 150, times my column total for with parents, 133, divided by my table total, 350, which is the exact same thing I just did using their proportions. So for the chi-square statistic, we calculated the exact same we did for a goodness of fit test. So our chi-squared statistic is the sum of our observed minus our expected squared over our expected. But this time, the sum is over all cells, not including the totals in the two-way table. So the degrees of freedom, because we now have two categories, our degrees of freedom are calculated by doing number of rows minus 1 times number of columns minus 1. And then to find the p-value, we use the chi-square statistic along with our degrees of freedom. So we find our p-value using our chi-squared CDF. So we go to second vars, and then we want to go to 8, which is our chi-square CDF, and we'll plug in our lower bound, our upper bound, which our lower bound will always be our chi-square test statistic, and our upper bound will always be 1E99, and then our degrees of freedom that we calculate using the formula above. So let's go ahead and calculate our chi-square statistic and our p-value and make a conclusion. So for our chi-squared test statistic, we will do 61 minus 51.8 51.857 squared over 51.857 plus 29 minus 24 squared over 24 plus 60 minus 74.143 squared over 74.143 plus 60 minus 69.143 squared over 69.143 plus 27 minus 32 squared over 32, and lastly 113 minus 98.857 squared over 98.857. So every value in our observed table minus its expected value squared over the expected value. That's going to give us a chi-squared statistic of 9.365. And then for our p-value, we go to second vars, and we go to 8. Now I do need to calculate my degrees of freedom. So my number of rows is 2. So 2 minus 1 times my number of columns, 3 minus 1, is going to give me degrees of freedom of 2. We don't count the total when we're counting our rows and our columns. They are not included in our calculation. So my lower bound will be the 9.365, my upper bound of 1E99, my degrees of freedom of 2, and we get a p-value of 0.0093, which we're going to compare. So now we can make a conclusion. So can we conclude there is a difference in the distribution? So our alpha was not stated, so we're going to use an alpha of 0.05. So when we compare 0.0093, it is going to be less than an alpha of 0.05, which means we are going to reject our null hypothesis. So we can say we have enough evidence to show that there is a difference in the distributions of living arrangements among males and females. So let's just go ahead and kind of summarize the chi-square test for homogeneity. So you're going to first determine your null and alternative hypotheses, which you are going to write with words. Again, we don't check the conditions. They are always going to be met. We're just going to assume they're going to be met, but all of your expected counts must be at least 5. It's going to be random. It's going to be independent. Then you'll calculate your chi-square statistic and determine the p-value. And then summarize your findings. So compare your p-value to your level of significance. Let's do one more example. So we want to know, is there a difference in the distribution of personality types across certain college majors? A college professor at a large university conducts a stratified study to determine which of the big 5 personality traits a person displays the most of. The results are shown in the table. So between business, engineering, and communication, those were our colleges, And then open, conscientious, extrovert, agreeable, neurotic were the big 5 personality traits. We want to know, does the data provide evidence that there is a difference in the distribution of personality types across college majors? Use a 5% level of significance. So our null hypothesis is going to be there is no difference in the distribution of personality types among the college majors. And our alternative hypothesis is there is a difference in the distribution of personality types among the college majors. Now we want to go ahead and calculate our expected values. So I'm basically going to recopy down my table, but I'm going to do some abbreviations here. So I'm going to do business, engineering, and communication. And then we're going to have, I'm going to do the abbreviations for our personalities, O, C, E, A, and N. I'm not going to go over and write the formulas. I'm just go ahead and write the values down. So using the formula that we discussed, you're going to do the row total. So for business, that's 151 times the column total, 87. And then we're going to divide by the table total, 440. So we're going to get 29.9. Okay, then our next one will be 151 times 78 divided by 440, which is 26.8. Then 151 times 90 divided by 440, which is 30.9. Then we have 151 times 95 divided by 440, which is 32.6. And then 151 times 90 divided by 440. So 30.9 again. And I'm not going to repeat this process for the engineering. So they have the same row total, which means all of my expected values are going to stay the same. So 29.9, 26.8, 30.9, 32.6, and 30.9. Lastly, we have communications, different row total, so different values. So we'll do 138 times 87 divided by 440, and we'll get 27.3. Then we'll do 138 times 78 divided by 440, which is 24.5. Then 138 times 90 divided by 440, which is 28.2. 138 times 95 divided by 440 is 29.8. And then lastly, 138 times 90 divided by 440 again, which is 28.2. So now we have all of our expected values. And just to save some time, I'm not going to write out the entire chi-squared test statistic formula here. I'm also going to show you how you can do it on your calculator here in a second, because if I look, I have 15 values in my table, which means I have to subtract from each value in my original table my expected value, square it, and divide it by my expected value. And that's 15 times. And that can be very time consuming. So like I would start with 25 minus 29.9, square it over 29. Then I would do 26 minus 26.8 squared over 26.8. And then I would keep going for the rest of my table. So to save some time for you have to write that out, I'm going to go ahead and do it. And we're going to get a chi-squared statistic of 14.4. Now I need to calculate my p-value, which means I need to know my degrees of freedom. So my number of rows, there are 3 minus 1, times my number of columns, of which there are 5 minus 1, which becomes 2 times 4, which is degrees of freedom of 8. So we go to second vars, and then 8. My lower bound will be 14.4. My upper bound is the 1E99, degrees of freedom of 8. And we're going to get a p-value of 0.0719, which when we compare to alpha is greater than 0.05, which tells us that we're going to fail to reject our null hypothesis, which means there is not enough evidence to show a difference in the distributions of personality types among the 3 college majors. All right, let's go ahead and talk about how to do a chi-square test for homogeneity on a calculator. So instead of entering our observed counts into a list feature, we're actually going to input them into a matrix instead, because a matrix is kind of like a table. So to do that, you hit second, and then matrix is the x to the -1 button. So if you hit that button, it will take you to a matrix, and then you go over to edit, and then you'll hit enter. And then you're gonna set up your rows and columns. And you do not have to do your totals, you just want your actual value. So we have the first value is our rows, so 3, and then our columns, 5. It's gonna create your matrix for you, and then you're gonna go ahead and input all of the data. If you hit enter after each value, it actually goes across in the rows. So make sure you are entering your data based on the row and not going down for your columns. So now that we have our matrix, we're gonna go to stat and then tests, and then we want to go to letter C, which is just our chi-squared test. And our observed is going to be A, which should be the matrix that you put your observed in. For our expected, it's going to be B, and that's where the calculator is going to store the expected. You don't actually have to calculate it ahead of time, which is really nice. And then you're going to hit calculate, and it is going to give you your chi-squared test statistic and your p-value and your degrees of freedom. So the nice thing here is you don't have to do your expected counts ahead of time. if you do it in your calculator. You still do need to include your expected counts on any assignment we do or assessment. You do need to calculate them, but once you run the test, if you go back into second and then matrix and you go to number 2 and then you hit enter twice, it will actually go ahead and give you the matrix with your expected counts. So you can do your expected counts table after you run the significance test if you want, but you still have to write down your expected values. So let me know if you have any questions about performing a chi-square test for homogeneity.